What does it mean when an earthquake ruptures in almost the same tectonic theatre that produced one of Indonesia's deadliest disasters? How much strain can a fault accumulate in 3 decades? And how closely can a new rupture resemble the earthquake that devastated Flores in 1992? And when a magnitude 7.7 earthquake tears through the shallow crust of the Flores Sea, only about 68 kilometers, or 42 miles, north-northwest of End, is it enough to regard the event as an isolated shock, or is it a reminder that one of the most dangerous thrust systems in eastern Indonesia remains very much alive? On August 14, 2026, at 21:58 UTC, the seafloor north of Flores answered with a violent release of energy. The earthquake struck at a preliminary depth of about 10 kilometers, or 6 miles, and its mechanism pointed towards shallow reverse faulting within the overriding Sunda plate. For communities scattered along the islands and coastlines of East Nusa Tenggara, the significance was immediate. For geologists, the location was even more revealing. The earthquake occurred in a region where the northward moving Australian plate presses against the Sunda plate at roughly 69 millimeters per year, or about 2.7 inches per year, while the enormous Sunda Trench lies roughly 350 kilometers, or 217 miles to the south. The earthquake was not simply a point on a map. It was the visible consequence of a much larger system of crustal deformation, one that has been reshaping the Banda Arc for millions of years. The memory of December 12, 1992, gives the August 2026 earthquake an unusually powerful context. On that day, a magnitude 7.8 earthquake struck the Flores region, producing severe shaking and a devastating tsunami. The USGS records at least 2,200 people killed or missing, including 1,490 at Maumere and approximately 700 on Babi Island. More than 500 people were injured and roughly 40,000 were left homeless. In Maumere, about 90% of buildings were destroyed or severely damaged by the combined effects of the earthquake and tsunami. Across Flores, approximately 50 to 80% of structures were damaged or destroyed. Other scientific assessments place the overall death toll higher, depending on how missing people, and later reports are counted, with one USGS-supported study assigning approximately 2,500 deaths to the tsunami itself. The catastrophe became a defining example of how a shallow earthquake on an offshore thrust fault can become vastly more destructive when vertical movement of the seafloor displaces seawater. That earlier rupture was not a random event in an otherwise quiet ocean. It occurred within the complex transition between the Sunda and Banda arcs, where the geometry of plate convergence becomes extraordinarily complicated. 34 years later, another large earthquake has struck the same broad tectonic system, bringing the Flores Thrust back into sharp scientific focus. The August 14 earthquake was located approximately 63 kilometers, or 39 miles, west-northwest of the 1992 epicentral region, according to the supplied event comparison, placing the two earthquakes close enough to demand attention without implying that they ruptured the exact same patch of fault. That distinction matters. Fault systems are not single cracks running continuously beneath the earth like lines drawn with a ruler. They are networks of faults divided into segments, bends, branches, barriers, and zones of varying strength. A large earthquake may rupture one section while leaving adjacent sections locked. Another earthquake decades later may strike nearby because the regional tectonic forces remain active, not because the older earthquake somehow scheduled its successor. The phrase "strikes again" therefore captures the geographic and geological connection, but it should not be interpreted as evidence that the 1992 earthquake directly caused the 2026 rupture. The deeper explanation is more fundamental. The Australian plate continues moving northward relative to the Sunda plate, and that motion continuously loads the structures capable of accommodating the convergence. The plate motion did not stop after 1992. Neither did the deformation of the Flores region. The architecture of eastern Indonesia helps explain why earthquakes here can behave differently from those along a simpler subduction zone. Farther west, along Java and Sumatra, the tectonic picture is dominated by the relatively straightforward northward subduction of oceanic lithosphere beneath the Sunda plate. The Sunda Trench marks the surface expression of that enormous convergent boundary. But as the system approaches the eastern end of the Sunda Arc and merges into the Banda Arc, Australia is no longer simply represented by a thin oceanic plate sliding beneath another plate. The Australian continental margin is being driven into the region. Continental crust is thicker and more buoyant than oceanic crust, so it does not descend into the mantle as readily. The result is a broad zone of collision and deformation rather than one clean, continuous subduction interface. USGS studies describe the Flores region as a transition between oceanic subduction to the west and continental collision to the east. That transition is critical. It helps explain why multiple fault systems operate above, beside, and within the subducting Australian plate, creating a tectonic environment where thrusting, strike-slip faulting, deep earthquakes, and crustal deformation can coexist within a relatively compact geographic area. The Flores Thrust, sometimes called the Flores Back Arc Thrust, is one of the most important structures in that system. It is not located at the Sunda Trench itself. Instead, it lies north of the main trench, behind the volcanic arc, within the overriding Sunda Plate. In simple terms, the oceanic and continental material associated with Australia is moving northward, while the Sunda side of the boundary is being compressed. Some of that convergence is accommodated at the main subduction boundary to the south. But not all of the deformation has to occur there. The overriding plate can shorten internally, and one of the principal ways it does so is through thrust faulting. The Flores Thrust represents one of these internal structures. Scientific studies describe it as an active long-back arc thrust, extending from the region north of Flores westward towards Sumbawa, Lombok and Bali. Its existence is a direct consequence of the fact that plate convergence does not necessarily concentrate all its movement on a single fault. That arrangement creates a geological paradox that is easy to miss on a conventional map. The most obvious plate boundary, the Sunda Trench, sits hundreds of kilometers south of the August earthquake. Yet the earthquake still reflects the same broad collision between Australia and the Sunda Plate. The stress generated by convergence is transmitted through the crust. When the rocks cannot deform smoothly enough to accommodate that stress, faults provide a pathway for sudden movement. A thrust fault forms when one block of crust is pushed upward and over another along a relatively shallow dipping fault plane. The movement can be only a few meters during an earthquake, but when it occurs across a fault surface tens of kilometers long, the combined effect becomes enormous. For an earthquake around magnitude 7.7, the rupture is better imagined as a broad patch of fault slipping than as a tiny point directly beneath the epicenter. USGS estimates for earthquakes of this magnitude and reverse faulting style indicate a typical rupture area of roughly 90 by 45 kilometers, or about 56 by 28 miles. That is an area comparable to the size of a substantial metropolitan region, except that the entire surface is moving at once deep beneath the sea. The August earthquake's preliminary focal mechanism is particularly important because it points towards reverse faulting. The available solutions allow for two possible fault geometries: one west striking plane dipping moderately northward, or another east striking plane dipping shallowly southward. Those alternatives illustrate an unavoidable limitation of early earthquake analysis. Seismologists can determine the direction and style of movement from seismic waves, but an earthquake's initial focal mechanism commonly produces two mathematically possible fault planes. Additional seismic data, aftershock locations, waveform modeling, satellite observations, and geological information can help determine which plane actually ruptured, yet both possibilities lead to the same broad conclusion. Compression played the dominant role, and the earthquake occurred within the overriding Sunda Plate rather than deep inside the subducted Australian slab. That distinction is crucial. The Australian plate is descending beneath the region, but the August earthquake occurred in the crust above that slab. It was therefore a back arc or upper plate earthquake associated with the broader Flores Thrust system, rather than a deep earthquake within the descending plate. The depth of approximately 10 kilometers or 6 miles makes the event particularly significant. A shallow earthquake places the rupture much closer to the surface, meaning that seismic energy has less crust to travel through before reaching communities. Depth alone does not determine damage, because shaking also depends on magnitude, distance, local geology, building construction, rupture direction and ground conditions. But a large earthquake occurring at shallow depth can produce intense ground motion across nearby areas. In an offshore setting, another concern emerges immediately. Vertical movement of the seabed can disturb the water column. That does not mean every shallow thrust earthquake produces a destructive tsunami. The amount and distribution of vertical seafloor displacement, the area of rupture, the depth of the water, and the geometry of nearby coastlines all matter. Nevertheless, the 1992 Flores earthquake demonstrated with devastating clarity what can happen when a shallow thrust rupture generates a tsunami close to populated shores. The August 2026 event therefore demands attention, not because a second 1992 catastrophe is inevitable, but because the underlying mechanism belongs to a class of earthquakes capable of producing both severe shaking and tsunami hazards. The 1992 earthquake remains one of the clearest demonstrations of that danger. Modern seismic analyses have estimated its moment magnitude at approximately 7.9, although different catalogues have reported slightly different values. Research by Beckers and Ley concluded that the earthquake was a shallow back-arc thrust event and estimated a rupture duration of about 70 seconds. Field observations following the earthquake documented extraordinary tsunami effects. Water penetrated inland, with studies reporting inundation distances reaching hundreds of meters and local run-up heights of several meters, while unusually high run-up of roughly 20 to 26 meters or 66 to 85 feet was documented in parts of the region. The tsunami reached the northern coast of Flores within minutes. That short arrival time transformed the disaster into a race against a wave generated almost immediately offshore. There was little opportunity for distant warning systems to compensate for the limited travel time. The geography itself became part of the hazard. Steep coastlines, bays, islands and settlements close to the sea could amplify the consequences of the incoming water. Babi Island became one of the most tragic symbols of the 1992 disaster. The USGS records approximately 700 people killed or missing there, while Maumere suffered catastrophic destruction and loss of life. The scale of the disaster revealed something more important than the size of the earthquake alone. Magnitude is a measure of released seismic energy, but human consequences depend on where that energy is released and what lies above the rupture. A magnitude 7.8 earthquake in an empty ocean can become a scientific event. The same magnitude near shallow water, vulnerable buildings and densely occupied shorelines can become a humanitarian catastrophe. Flores demonstrated that distinction decades before tsunami, early warning systems, and modern seismic networks became as sophisticated as they are today. The August 2026 earthquake occurred in a region that has not been dormant during those intervening decades. According to the supplied seismic assessment, 37 other earthquakes of magnitude 6 or greater have occurred within the broader area since 1950, including 5 other earthquakes of magnitude 7 or larger within approximately 250 kilometers or 155 miles of the new event. That frequency is not surprising given the active convergence between Australia and Sunda. It is, however, an important reminder that the Flores Thrust is not a geological relic left behind by the 1992 disaster. It remains part of an active deformation system. In 2018, for example, A magnitude 6.9 earthquake near Lombok was associated with the Flores back arc thrust. USGS analysis found that the region was undergoing north-south convergence at roughly 70 millimeters per year, or about 2.8 inches per year, and concluded that the earthquake was consistent with southward-oriented thrusting along the back arc system. The pattern becomes even more revealing when earthquakes are viewed across different depths. A magnitude 7.3 earthquake in the Flores Sea in December 2021 occurred at a depth of approximately 14 kilometers or 9 miles, but its mechanism was strike-slip rather than thrust faulting. USGS determined that it occurred within the overriding Sunda plate, again demonstrating that the upper plate can accommodate convergence through more than one style of deformation. Meanwhile, much deeper earthquakes in the same broad region can occur inside the subducted Australian slab. A magnitude 7.0 earthquake in 2015 occurred roughly 552 kilometers, or 343 miles, beneath the Flores Sea, and was interpreted as strike-slip faulting within the descending Australian plate. These events may occur within the same broad tectonic system, but they represent very different physical processes. The August 2026 earthquake belongs to the shallow upper plate category, making the Flores Thrust the key structure for understanding it. That distinction also explains why the Flores region cannot be reduced to a simple picture of one plate sliding underneath another. The convergence between Australia and Sunda is being distributed across several structures. Some motion occurs at the main trench. Some is absorbed by deformation within the overriding plate. Some is expressed through the Flores and Wetar thrust systems. Strike-slip faults accommodate horizontal shearing. Deep earthquakes occur within the descending slab. Continental collision farther east changes the geometry again. USGS mapping of the region identifies a broad deforming zone around the Sunda-Banda transition rather than a single uniform boundary. The crust beneath Flores itself is also unusually substantial, with receiver function studies estimating crustal thicknesses of roughly 38 kilometers or 24 miles beneath Flores and neighboring regions. Such variations in crustal structure matter because they influence how stress is transferred and where earthquakes can occur. The Sunda Trench remains the enormous engine behind this regional compression. Extending for roughly 3,000 kilometers, or 1,860 miles, along the southern margin of Indonesia, the trench marks the zone where the Australian and Indian oceanic lithosphere descends beneath the Sunda plate. But the Flores earthquake occurred far to the north of that trench. At first glance, the distance might appear to separate the earthquake from the principal plate boundary. Geologically, the opposite is true. The distance demonstrates how deformation can migrate into the overriding plate. Imagine pushing a thick, rigid object against another object. The pressure does not necessarily produce movement only at the point of contact. The material above the boundary can buckle, shorten, and fracture. On a geological timescale, those movements can build mountain belts, uplift islands, and generate earthquakes along faults located far from the trench itself. The Flores Thrust is one of the structures created and maintained by this compression. The seafloor is particularly important because much of the Flores Thrust lies offshore. On land, a fault may leave visible scars, offset streams, tilted terraces, broken ridges, or abrupt changes in elevation. Offshore, the evidence is hidden beneath water and sediment. Yet a large thrust earthquake can leave a geological fingerprint on the seabed. A section of seafloor may be lifted, creating a submarine ridge. Another section may drop. Sediments can be folded or fractured. Repeated earthquakes can build large underwater scarps over thousands of years. Modern multi-beam sonar and seismic reflection surveys allow researchers to map these features with extraordinary precision. Recent work on the Flores and Wetar thrust systems has identified seafloor structures and seismic patterns that support the interpretation of active deformation and significant tsunami hazard. For researchers, the most valuable question now is therefore not whether the Flores Thrust has returned, but what the August rupture reveals about its structure. Did the earthquake rupture a known segment of the thrust? Did it break through an area previously identified as locked? Did it terminate at a geological barrier? Did the rupture extend towards the region affected in 1992, or did it remain separated from that older rupture zone? Are the aftershocks concentrated on a single fault plane, or are they activating a network of secondary faults? These questions can transform the event from a frightening headline into a much more precise understanding of regional hazard. They also help identify which areas may deserve closer attention in future seismic and tsunami planning.